Welcome back to our next session, EME Model Mayhem by me. And so just to give some background information, we're talking about heart valves today. And so heart valves are tissue/leaflets that are located in the heart. And the main function of those leaflets are to provide unidirectional flow of blood through the system. There's systemic circuit and pulmonary circuit in the body. And so there's four main types: the mitral, aortic, tricuspid, and pulmonary, as seen here in the right. And so when you look at the classification of the structures for these heart valves, you'll notice different compositions, such as collagen, elastin, and glycoaminoglycans. And so in particular, this gives it the viscoelastic properties of the valve. You also notice within the heart some larger support structures, including the chordae tendineae, since these valves, they're attached to the chordae tendineae. It allows it to, gives it more structure. And that these chordae tendineae also attach to papillary muscles in the ventricles. And so you won't want your heart valve to function for a long time. But there's a lot of factors that go into why it might wear down. One of the main factors being stenosis and regurgitation. And so from these main categories, you have other ramifications that include endocarditis, which is a bacterial infection in the heart, connective tissue disorders, rheumatic disease, and calcification. And so because of the way the heart works, the aortic and mitral valve is usually the most affected, since you have this pumping action in the systemic circuit of the circulatory system. The left side of the heart receives more pressure, usually. But it can affect any other type of valve, including the tricuspid and pulmonary. Some current treatment modalities that are used to address a disease of a valve, in particular aortic valve, could include mechanical, bioprosthetic, and donor tissue. And so for today, we'll be modeling the Abbott Trifecta GT 8 heart valve. But you can notice here to your images on the right, other types of valves that came before bioprosthetic valves. And so one of the predecessors include the cage ball, which is basically, as it's shown, it's just a ball in a cage. And so there were pros and cons with this. One of the pluses includes that it provided satisfactory blood flow for being one of the early prototypes, but then involved other complications such as lysing of blood cells of hemoglobin and accelerated clotting. So you don't want that on your device. And so the further developments include the monoleaflet and bileaflet mechanical heart valves, which are made of pyrolytic carbon to prevent clotting onto the device. And so for bioprosthetic heart valves, they're usually taken from porcine or bovine tissue in animals, and they're sutured together or sewn together in a way that simulates the native shape. So for today's design, we'll be looking at the Abbott Trifecta. If you notice to the images, such as these, it has a scallop design covered in polyester covered titanium, which gives it a shape. And I've done some research, and actually this is, there's a lot of iterations with this design, a lot of continuous improvements going on as early as 2007. So today we'll be modeling something close to the 2020 design. It does not include the new holder or the holder for the heart valve. So I think the holder, what it does, it allows it to retain its shape, since this is composed of different tissues sewn together. And this is information available online with the different specs. And this will be the model that will be designed. So from here, let's jump over to SolidWorks. So as I mentioned earlier, some features you can introduce yourself when you use SolidWorks is family tree to the left. And so this family tree will allow you to see the progression of the part as it's being made, from the earliest to latest features or parts incorporated. But the first thing you want to do is start a new part. So here you have a new part, and you can, in the SolidWorks, you can create part assemblies and drawings. So today we'll be focusing on parts. And usually when you have multiple parts, you make an assembly out of it. And the first thing you want to do before you begin any part is to make sure your units are correct. So we'll be using MMGS, which stands for millimeters, grams a second. So that's the metric system. And you can press spacebar on your keyboard to get this cube for the different orientations. So we're going to start at the top orientation, and we're going to show our top plane. So if you notice the design of the heart valve, it has a scallop shape, what they call it, for the base. And so the reason they say they do this is to allow it to shape to the contours of the native tissue. So let's find a way to simulate that. And we begin with sketching on the top plane. We'll sketch a circle. And the dimensions for this, if you remember on the PowerPoint, it was 23 millimeters. Then there was a second one for the outer diameter of the annulus, or the cuff. So the cuff will be the part that attaches to the native tissue. And so we have 23, 28. And we'll throw in an intermediate one, 26, in between 23 and 28. Let's arrange them by order. And then we're good to go. So then you can press D on your keyboard to get this. Okay. Click OK. And that's our sketch for now. So next thing you want to do is you want to extrude this. Go to Features, Extrude Boss Face. And so you'll be extruding this part. We'll extrude upward 13. And we'll extrude downward 5. So now I have a cylinder. The next thing you want to do is you want to be able to simulate that scallop feature. And so there's a nice function in SolidWorks called the curve function, or the equation-driven curve. And so the equation-driven curve is going to allow you to write a mathematical equation and then make a curve out of it. So let's go ahead and do that. The first thing you want to do is, for equation-driven curves, is you want to have a 3D sketch. And so right now, we made a cylinder out of a 2D sketch because it's on one plane, the top plane. But when you make a 3D sketch, you're defining it in 3D. And so it brings in a bigger variety of tools that you have at your disposal when you have a 3D sketch versus having a 2D sketch. So we here declared a 3D sketch on our top plane. And now we're going to include an equation-driven curve. And so for our equation-driven curve, we have our y, x, and z. Let's type in the function to find this shape. The shape for this scallop cuff. So what do these functions mean? These functions mean that basically we're giving it parameters from half pi minus a small value to 1.5 pi minus a small value. The reason why you include the small value is so that doesn't give an exact pi answer, because I think that's undefined. But then you have from these parameters T1 to T2, you want to plot these curves. And so once you have these curves, click OK. And what we have right now is a cylinder with a function-driven curve, or an equation-driven curve. So what do you want to do next? This is what you want to do next. And we did it in a way so that it goes through half the cylinder. So now let's hide our top plane, go to our front plane. Let's hide this solid body. So now we have our curve, and we have our front plane. Let me show you another trick you can use. Okay. You want to click OK on your sketches to approve it before you move on. Let's go ahead and repeat that in one moment. Select your top plane, you do 3D sketch, and then from there, you do equation-driven curve. And thankfully, I have the notes written here. I figured out the functions needed to get this curve. So let me talk to you a bit about these functions. This is basically going to say on the x-axis or on the x orientation, make this function. On the y, this is the most important one. You want to have a 2 sine 3t. So the 2 is going to give it the amplitude, and 3t is going to be the number of repetitions if it goes full revolution around the cylinder. And you want the last one to be cosine. For parameters, pi. So we're starting at half pi and we're ending at 1.5 pi. If we began at 0, then we would begin here where my cursor is right now, and then we would finish all around at 2 pi. You'll notice because of this y function, yt function 2 sine 3t, it's going to go around the entire cylinder 3 times. So it's going to have like 3 peaks in a minute once you see. So we click OK, and that's good now. Now we accept the sketch, and now we accept the sketch. What we want to do now is we want to go to our front plane. And our front plane, we're going to make a sketch. Here we go to convert entities, and we're going to select the curve-driven function we have, or the function-driven curve. We're going to project it onto our plane for the front plane. And so now we made a kind of like a cross-section of our function-driven curve on our front plane. Now we're going to do another function called silhouette entities, and we're going to make this. We're going to select this body. So we selected this body, and now let me hide it. So that body is hidden, and we have a sketch, kind of like a cross section of our equation-driven curve. Let's go ahead and include a line here. And set these 2 lines parallel. And a dimension constraint. So there we have our cross section, marker body, and now let's include some reference geometry. One axis. So include an axis with our front and right planes. And this will be helpful later when we're using different features, because at this reference geometry, you can orient stuff around that axis. Cool. Let's do a sweep. So allow me to introduce you to the sweep function. The sweep function is basically going to get a sketch profile and revolve that sketch profile along a line. Along a particular contour. And so we'll be using this sweep function to simulate the outer cuff. So if you notice, the outer cuff reaches to 28 millimeters. So I'll give this as a diameter of 2 millimeters. That way we can reach that 28. There we go. We have our outer cuff, and we have our main body, which is a cylinder. So what we want to do now is let's hide these bodies. And bring back our boss extrude. Let's create an extrude cut using our sketch 3. Sketch 3, and now we're going to cut through our cylinder. So the end result would be a cross section through the cylinder that you just cut. What's next? So now you'll notice we have our cylinder and we have the shape of the scallop curve during function. Let's go ahead and include a reference geometry. And this reference geometry will be helpful in creating the lofts or the ridge for this cuff, because the cuffs are sewn together, and so it has a polyester covering or a polyester coating that around this titanium band. Let's go ahead and finish making our reference plane. And so this reference plane, you want to set it at the beginning of the curve during function. So we bring back our curve during function. And we set this dot as the initial point. So now this front plane is going to intersect this curve during function at that point. So that's good. What we want to do is create a geometry that is offset from that at an angle. So this is where the axis comes in. We declare front plane, and then we declare our axis. And then we just find the appropriate angle for it. In particular, we want it to be 1.5 degrees off from the axis. So it should be 360 minus 1.5. 358. Yeah, that's fine. We bring back our body. There's our solid body, and there's our sweep. So now we're going to sketch onto the sweep. Click sketch, and we're going to choose a face. We're going to use this face that we use for the sweep to sketch on. We had our front plane, and now we have our plane 1, which is a plane that we made at an angle to the front plane. We're going to sketch on that one too. And we're going to set this circle coincident to the curve, because we want it to be along the curve that we had. So we go here and click pierce. It's not the one we want. Gotcha. There we go. So we're drawing on the plane that's an angle, and we set a coincident. So I guess before we were just drawing on plane number 2 and plane number 1, but it was really the front plane. But this one is at an angle, so, and you'll notice because this is the angle, it makes it 1.5. 1.5 angle of a difference. So let me introduce you to a new feature that you can use called the loft. And the loft is going to make a continuous connection between two sketch profiles. And so we selected our two circles as our sketch profiles for the loft, and we're going to set some constraints so we can round the shape of the loft. That's good. And so once you're satisfied with the loft, you click OK, and it should create this kind of fillet-looking parts. So from here, what you want to do is you want to make a mirror. You want to mirror this body. So you select their face or a plane to mirror, and you select their bodies to mirror. In this case, it's the loft 1. And you have a loft on both sides. So what's next? Now you have this cuff, and you want to be able to bring this cuff throughout the entire part. So we're going to incorporate a feature called curve-driven pattern. There we go. That's better. So now we have 40 equally instance spaces of our mirrored body across the curve. We'll bring back our sweep function. Now it's starting to look more like a cuff. Let's go ahead and edit our feature a bit. There we go. And so now we have a cuff throughout half the cylinder. Now we're going to repeat this for the other half. So mirror slash face. Select the bodies that we want to mirror. We have 82 bodies. $82 times the charm. So here we have our sweep. And then let's click OK. And so that will take us from 82 to 160 something. 164. And now we have the cuff throughout the entire cylinder. Looks nice. And so now you'll notice your family tree is starting to get bigger. Let's do a quick save. So just to summarize what we've done so far, we've done a curve-driven function, or a curve equation-driven curve, to simulate the outer cuff of this annulus, this heart valve, and we included the details by incorporating a loft function and then mirroring along the axis or along the planes. So now we're going to focus on is creating the valves. And to do that, allow me to introduce you to something called a spline. But first, let's clean up this space that we have here. Let's hide the sketch. Let's hide this plane. And we'll hide this sketch. Maybe this is where we're at it too. And back our top plane. Let's sketch on it. Now we'll sketch on our top plane. Sketch on the top plane. Six. Awesome. So we put a sketch on the top plane, and now we're going to make another sketch on this surface area on top of our cylinder. So we drew a reference line, and so these dashed lines, they're called construction geometry, or reference lines. And the solid lines, they're called actual solid lines. Those are active. They make up your part. But you can use these reference line to help you with reference geometry or to do mates. So now we're going to be modeling the top portion of the valve. If you look at it from the top, from an aerial view, then you'll notice it has a tri-leaflet feature. And so these tri-leaflet features has a base on top, and we're making that cross section with that top base. And so once you made the general shape for this tri-leaflet feature at the top of the base, then you can incorporate it. And you'll notice these will be the support structures, and they are aligned to the top of these peaks on the curve-driven function, the function-driven curve. Let's go ahead and incorporate that spline feature. So we're going to make a plane first of all, reference geometry, and then go to plane. And we're going to select this edge, and then this edge. So the two sketches we had, one for the top face and the one from the bottom face, those are going to make a plane at 3 points. All right, so we have the plane at 3 points, and now we can sketch on it. We're not just going to make an A sketch, we're going to make a 3D sketch, if possible. So we select our plane number 5, do a quick save. Select our plane number 5, and do a 3D sketch. And here is where I introduce you to the spline feature. So before we did an equation-driven curve, or a function-driven curve, now we're going to do a spline. And we're going to select the spline between this point, the point we selected down here, and this point. And once you're satisfied, you click escape. And you'll notice, instead of an arc, it does a spline. Particularly, splines are powerful because they're not defined by a certain geometry. If you want to have an arc, then the arc will have constraints related to arcs. Same thing with ellipses. They have a set shape or geometric shape, geometric constraints. Same thing with 3-point arc slot, or hyperbolas or parabolas. But a spline can be whatever you want. The only inputs that you have in a spline that you need to consider are the curvature, the spline curvature, and the direction. Let's go ahead and go to 3D Sketch and edit this curvature shape. And so by splitting entities, we're saying, hey, we want to split this spline. And so now that the spline is split, we're going to be able to access that curvature. So we're going to stretch this curvature even further, make it a wider spline. And now we made it wider. Let's go ahead and click accept. So what do we have now? We have a surface spline right here. And we're going to make a surface loft, or lofted surface between this curve and the spline that we selected. To view this surface loft, let's actually hide this body. So now we just have our curve and our sketches. So we go here, loft, create lofted surface. And you'll notice the lofted surface is going to be connecting from our spline sketch to this sketch we have here for this fillet. So I'm trying to connect that as best as possible. Let's add some constraints. Sometimes the constraints won't help you as much. So let's just leave it none. Let's bring back our bodies. And so now you'll notice we have a solid body category and a surface body. The surface body was the surface loft we just made. And so we just played in SolidWorks and made a surface body. And there's other ways you can manipulate surface bodies into being solid bodies, which I will show you one way here. Let's go back and bring solid body. And now we'll repeat this surface body along the circle. So let's go to circular pattern. Our direction will be this circle. And the features, in this case the body, we want to repeat is the surface body here. Surface loft 1. And now when we hide our solid body, we have 3 spline surface lofts. Kind of cool. So what's next? Allow me to show you one application of how you can use surface bodies to affect solid bodies, particularly as a split tool. So the surface body we just made is going to now cut the solid body. of the cylinder at the contour that we're looking for. Let's go ahead and see what this looks like. And notice now, our solid bodies include 4 split bodies at the bottom. And so we have split 1, let's hide it. Split 2, let's hide that one. Split 3, and split 4. And so we got our cylinder and split it to remove the bodies we didn't want, or to remove those cross sections on top. And now that we have surface bodies, let's remove that. And we'll just keep the solid bodies that we want to work with. Another sketch here. Cool. So what's left? What's left is, let's do something called shell. Let's give shell a try. So shell is going to make a hole, or create a shell out of this contour between this face and this face. Let's see if this works. All right, so shell does not work. One reason why shell might not work is because of the split bodies tool. But there's a way around this. Let's go back to our sketch. Sketch 19. Let's create an extrude cut from it. And so in reality, when they manufacture this, you're really sewing different surfaces together of porcine tissue, bovine tissue, and you're suturing them onto the cuff. So inside it would be hollow, but for this application, we're going to extrude this all the way down. Through all. And so we're going to extrude it through all, and we're going to add a 1 degree draft to it, outward. Cool. So what we have the leaflets right there using the spline feature. We have our extrude. We're just missing fillets. So fillets, rule of thumb, you want to start with the highest fillets and end with the lowest fillets. So choose the biggest edges that you have and start with those. For the fillets, the standard is circular fillet, although you can use other fillets as well, other fillet profiles. Looks more like a trifecta. Let's go ahead and continue with our smaller fillets. So there you go for let's. And if we can, let's repeat this for the bottom side as well. Actually, let's find a way to make the annulus here reasonable. Because right now there's this guy would have stenosis, or this person would have stenosis. So it says here the tissue annulus diameter is 23. So let's go ahead and add a 23 millimeter loft down here. And so you can loft base and you can also loft cut. The first thing before we add a loft, let's make a plane so we can reference this side. Top plane. I'm going to bring this plane as close as possible. To our annulus. All right. And just let it load. Do a quick save. And now we'll do a sketch on this plane. And what was it, 23? Add a 23 annulus. And then we'll add another one up here. That way, we can create a loft from 2 sketch profiles. So we're almost there. Now I just need to go to lofted cut and select our sketches to loft. And so it's going to cut into the body. What do you have left? We have a pretty smooth loft cut. How about that? And so now this would have clearance. And we can add fillets. Starting from the big ones to the smaller. And so we selected right now, you'll notice we selected all the edges at once. That feature, when you select the fillet, it gives you the option of choosing between available fillet options. And it saves you so much time instead of having to click each particular edge you want to fillet. So what's left? Now comes my favorite part, which is basically applying material and color properties. So do a quick save, and we go jump over to Render Tools. Render Tools allows you to edit your appearance, edit your scene, and create a preview window of your render and then your final render. Let's go ahead and edit our appearance here. Give it a white low gloss plastic touch. Make it look nice. And click OK. And go to edit scene, and we edit our scene. Let's select reflective floor black for the scene. Click OK. Looks nice. So then we just pop over to the preview window. This is how it looks like. So once you're satisfied with the preview window screen, you can go ahead and initiate the final release render. Let's go ahead and do that. We select final render, and this would initialize the rendering process. And so now you notice once you have your finished your render, this would be the window space that you would have with your output. And save your image. And so that image is now saved. Let's go ahead and jump over to SolidWorks. That's pretty much it for this session. Some key takeaways from this session include learning how to do splines, learning how to split bodies, how to create curvature and functions, which is a new feature to me, and how to professionally make this presentable using rendering options that include edit appearance and edit scene features. So if you like it, please like and subscribe, and I'll see you guys on the next one. Take care.